Welcome to the discussion of forces and the laws of motion. Okay, so if we're going to start talking about forces, then we need to know what the definition of a force is. So a force is a push or pull exerted on an object, and this force is an interaction with the environment. We often split things into what we call systems and environments. Systems are the things that are being acted on, and the environment is the thing that is acting on the system. A force can cause a change in velocity. Okay, so these are a couple of things that you need to know for sure. A push or pull can cause a change in velocity. The SI, or standard unit for force, is the Newton. Of course, that's named after Sir Isaac Newton. And then if we're going to define a force, it is going to be a 1 kilogram object accelerating at 1 meter per second squared. And that's going to give us the actual unit for a Newton. That is 1 kilogram times meter per second squared. So altogether, a Newton, so 1 Newton, is equal to 1 kilogram times meter over second squared. So obviously you can see why we would rather say Newton instead of kilogram meter per second squared. Alright, there are two different kinds of forces. There are contact forces and field forces. Contact forces require the objects to touch each other, and field forces do not. So examples of contact forces are if something is being hit or pushed or pulled, and we often will group these things into what we call an applied force. And then we have other things like tension force, friction, buoyant force, and we'll talk a little bit more about all of that stuff here in just a second. The field forces would be gravity, the magnetic force, or the electrostatic force. And oftentimes we will group these last two things into the electromagnetic force. Alright, so now we are going to talk about force notation, and that's just how we write down our different forces. We've got F sub little g, which is the force due to gravity, and that is the same thing as weight. Okay, the force due to gravity is an object's weight. Remember, we talked back in chemistry and earlier this semester in physics about how mass and weight are two different things. Mass is how much matter an object has, and weight is that mass, or that amount of matter's relationship with gravity. Okay, so this is the formula for the force of gravity. It is mass times the acceleration due to gravity, which is what A sub g stands for. Sometimes you'll see it just as little g. Okay, now little g is a positive value that's equal to 9.81 meters per second squared. That'll show up a little bit later on in the video, but I thought I would just show it to you now as well. Okay, so the next thing we have is the normal force. In physics, the word normal means perpendicular, okay, so at 90 degrees. So a normal force is one that is 90 degrees to the surface that it's sitting on. So for example, if we have a countertop or something, and you have a box sitting on that countertop, the normal force is going to be exerted because of the contact with the counter. Okay, this is one of those contact forces. So the box is sitting on the counter, and the counter is pushing upward on the box, and that is going to be 90 degrees from the surface. So this is the normal force. Okay. Alright, the next thing we have is F sub T, or F sub capital T actually, and that is a tension force. The tension force will be a pull, and that it will be transferred through a rope or some rope-like object, which would be, a string or a cable or something like that. The next type of force we have is frictional force, and frictional force is represented by this, kind of fancy looking F, which something like this if we blow it up a little bit bigger. You'll also sometimes see it written as F sub F, and that's the force of friction. So either way, I usually always write it with that, kind of fancy F. The frictional force is a force that exists between two objects when they contact each other. So this is a contact force. And friction is always opposite of the direction of the motion or the tendency of motion for an object. It has its own formula, which is mu times the normal force. This little symbol right here is called mu. That's a Greek letter. And the reason it's called mu is because when we write it, it looks like this. And it sort of looks like an M, and it sort of looks like a U. So it's called mu. And mu is the coefficient of friction. All right? And we can have a static coefficient of friction or a kinetic coefficient of friction. Static means that the object is sitting still even though you're pushing on it. So think about a heavy object like a car or something, and you go and start pushing on the car. Maybe the car's in neutral and you're trying to help somebody get to a gas station, and you go to push on the car and you're applying a force to the car, but the car's not moving yet. The car is resisting the tendency to move. Whatever direction you're pushing in, the car has a tendency to move in that direction. However, static friction is preventing the car from moving yet because you have not applied enough force to get the car moving. Once the car starts moving, then we'll have kinetic friction. And remember, kinetic means to move. So once the car's moving, it'll have kinetic friction, and that will be in the opposite direction of the car's motion. Okay? So you definitely need to know the formula here for friction and be able to apply it. We have a special situation here with the static coefficient of friction. If you want to calculate the static coefficient of friction, it is equal to the tangent of theta. So let's imagine for a moment that we've got some kind of a ramp or an incline, and you put a box on that incline, and we then measure the angle at which the box first starts to slide down the ramp. At the exact moment that the box slides down the ramp, we take a look and see what this angle is down here. And if we do that correctly, we can plug it into this formula, take the tangent of that angle, and that will tell us the static coefficient of friction between the box and the surface of the ramp. Okay, we can calculate the mu s. Now what I just did here is what you'll often see. Anytime they're trying to tell you about the coefficient of friction between a surface, let's say this box and this surface, they'll do a little arrow from in between those two surfaces, and they'll tell you the coefficient of friction is equal to whatever. Okay? Alright, so let's talk about where friction comes from. That would be this over here. Every surface has peaks and valleys to it if you zoom in on it close enough. And as those peaks and valleys rub in contact with each other, it slows them down. It resists the motion. So if you have larger bumps, like if you were talking about sandpaper or something, then you're going to have a lot of friction. If you have, ice cubes rubbing against each other, then they don't have very deep valleys or very high peaks, and so there's less friction there. So here's another example or picture of that static friction and kinetic friction. So here we've got, a rock, and someone is pulling on the rock with this applied force, but the rock is not moving yet. That means they're not pulling on it hard enough to get it to move. The thing that is keeping it from moving, even though they're applying a force to it, would be a force of friction. Now, what kind of frictional force is keeping the block in place? Hopefully you said static friction. Okay? Now if we look over here, they're applying a larger force, and now the block, or the rock, excuse me, is moving towards the right. What kind of friction would be opposing the motion now? Okay, this would be kinetic friction. You'll also see, and I should have told you maybe a little bit earlier, but you'll see these little symbols above any of the forces, and of course you should be used to this by now because we did it all through kinetics, but force is a vector quantity, which means it has magnitude and direction, and so we need to put our vector symbol above our forces. Alright, down here we have a graph and a table. This is a graph of the different kinds of friction versus an applied force. So this is saying that we can be pulling or applying a force to an object, and we pull, and the resistive or frictional force gets higher and higher and higher until we reach this maximum point right here at the very top. That is the maximum static friction. And then after that point, the object starts moving and the friction goes down. So static friction is always higher than kinetic friction. Okay, so if we look over here in our tables, different surfaces, because of the peaks and valleys that they have on a microscopic scale, are going to have different amounts of friction. So we have different coefficients of friction between different surfaces. So we have a static friction and we have kinetic friction. And if you'll look down the list for each of them, you'll notice the kinetic friction is always less than the static friction. And you'll also notice that none of these are higher than 1. And so it is very rare. It can happen. You can have a coefficient of friction larger than 1, but it's very rare. It doesn't happen very often. And so it would be extraordinary circumstances that we would have that. But anyways, you'll notice that kinetic coefficient of friction is lower, and that goes hand in hand with this graph here. The kinetic frictional force is less than the static frictional force, just like the kinetic coefficient of friction is less than the static coefficient of friction. Alright, back to some more of our force nomenclature. We have F sub capital B, which is the buoyant force. That's an upward push on an object when it's in a fluid, like a liquid or a gas. So that's why when you go swimming or whatever, you feel like you're lighter than normal, and that's because the water that you're swimming in is actually applying an upward push on you, and so it's kind of canceling out some of your weight. We then have F sub lowercase e, that's the electrostatic force, and that's between two charged particles, like protons and electrons and things like that. We will deal with this at the very end of our physics course, but we will get there. Alright, then we have what we call the net force. This is the overall force of a system when all of the forces are added together. That's very important, okay, when all the forces are added together. And then the next important thing is the net force is always in the same direction as the acceleration. That's hugely important. You need to know that. Alright, then we have a situation where we can have an object in equilibrium, and these are the two requirements that have to be met to make that object be in equilibrium. And that means, equilibrium means when the sum of all the forces in the system are 0. In other words, the net force is equal to 0. Okay. And that's 0 newtons. Okay, so if the object is at rest, that is one situation in which it's in equilibrium. And then the next one is if it's moving at a constant velocity. And there is something that's the same about both of those situations, and that is the acceleration would be 0. If you're moving at a constant velocity, you have a 0 acceleration, and if you're sitting still, you have a 0 acceleration, and so that will put the system in equilibrium. Okay? Alright, so let's move on to Newton's 3 laws. Newton's first law has its own special name. This is actually called the law of inertia. Okay, so law of inertia. And inertia is just an object's tendency to resist change in velocity. Okay, so let's write that down. So that's the first one, and it is an object at rest stays at rest, and an object in motion stays in motion until acted on by an outside force. And so that kind of goes hand in hand here with inertia, resisting a change in velocity. Okay, it doesn't want to slow down and stop if it was already moving, and it doesn't want to move if it was already sitting still. Okay, then we have Newton's second law, and this is perhaps going to be the one that we focus on the most in this course, and that simply gives us this equation here, that force equals mass times acceleration, and specifically that is the net force. Okay, net force. Alright, and then we have the third law here, and that says for every action there's an equal and opposite reaction. So we have here the force of object 1 on object 2 is equal and opposite to the force of object 2 on object 1. Okay, then we have some proportional statements down here that we need to take care of. When mass is constant, the force is proportional to acceleration. Here's what we mean. If we take Newton's second law, and anytime you have an equation that has a constant in it, you can ignore the constant for the purposes of proportionality. So the mass here won't count because they said it's constant. Alright? That means that the force is directly proportional, that's what that symbol means, to acceleration. So that means if the force goes up, then the acceleration will go up. If the force goes down, then the acceleration will go down. Alright, so the next one says when acceleration is constant, then force is proportional to mass. So let's take a look at that. Same equation, it's going to be force equals mass times acceleration, but this time we're saying that the acceleration is the constant. The acceleration stays the same. That means then that the force is directly proportional to the mass. The reason that it's directly proportional, by the way, is because both of these are in the numerator. Okay, so we're going to say, you know, if the force goes up, then the mass has to go up, and vice versa. And finally, if the force is constant, then the mass is proportional to 1 over the acceleration, or in other words, the mass is indirectly proportional to the acceleration. Here's what we mean. We take the same formula, force equals mass times acceleration, and this time the force is the constant. Now, we can't leave these two things on the same side of the equal sign because then we can't tell anything to do with proportionality. So, I'm going to go ahead and divide by the acceleration on both sides. So that cancels out over here. Over here, that's the same as having a 1 times force, right? So we could say that 1 over the acceleration is proportional to the mass. In other words, the mass is indirectly proportional to the acceleration. So, if the mass goes up, the acceleration goes down, and vice versa. Alright, so here's a question. It says that gravity is accelerating the mass of the hanging mass over here towards the center of the Earth. What is the force due to gravity on the hanging mass? Okay, well, up above, earlier in the video, we had the force due to gravity had its own formula, and that was mass times the acceleration due to gravity. And I told you what the acceleration due to gravity was. It was a positive 9.81 meters per second squared. So, we take the mass of the hanging mass, multiply it by the acceleration due to gravity, and we get 4.905 newtons. Now, remember I told you that force is a vector quantity. It's got magnitude and direction. This is the magnitude of the force, and now we need the direction. Gravity always points downward towards the center of the Earth. So our final answer here needs to be that the force of gravity is equal to negative 4.905 newtons. And that negative sign there indicates that it's pointing downward. And then I guess we could go one step further and take into account significant digits. We only have one sig fig over there, so we would probably say that it is negative 5 newtons. Okay? Now, remember, the force of gravity is the weight of the object. We just calculated the weight of that hanging mass to be 5 newtons. Weight could be in pounds or newtons or foot-pounds, or there's all kinds of different units out there for weight. The one that we are using here is the SI unit, newtons, but your weight, that you're used to seeing, is measured in pounds. We could convert your weight into newtons if we wanted to. Okay, so the next thing is the universal gravitational equation, and yes, you must memorize this. Okay, this has to be memorized. I also want you to do one more thing. Add in absolute value bars here and here, please. Okay, so the absolute value of the force of gravity is equal to big G times m1 times m2 divided by r squared. Of course, force is going to be calculated in newtons. Big G is what we call the gravitational constant, and that's this value right here, and it will always be this value right here. That's why it's a constant. Okay. M1 is the mass of the first object. It's usually going to be the bigger object. M2 is the mass of the second object, usually the smaller object. And R is the distance between the centers of the two masses. It is not the radius, it is the distance between the center of the first object to the center of the second object. Everything in the universe that has mass exerts a force of attraction on everything else that has mass. When you drop your pencil and it starts accelerating down towards the earth, that's because the earth is exerting a force of attraction on your pencil. But your pencil is actually also exerting a force of attraction on the earth. So the earth actually moves towards your pencil just like your pencil moves towards the earth. Now obviously we can see the pencil moving a lot more than we can see the earth moving because the earth has so much more mass. The amount that it moved towards the pencil can't be distinguished with the human eye. Okay, so that's this equation right here. Let's work a practice question. Okay, so the distance from the surface of the Earth to the Earth's center, so that would be this distance right here, okay, is 6.38 times 10 to the 6th meters. Okay, in other words, that's the radius of the Earth. So I'm going to kind of color code that there so you see that. And the mass of the Earth is 5.98 times 10 to the 24th kilograms. What is the force of gravity on a 1 kilogram mass sitting on the surface of the Earth? Okay, now a couple of things here. Obviously, a 1 kilogram mass is not being drawn to scale there. If it was, you wouldn't even be able to see it. I couldn't even make a mark tiny enough on the screen to replicate, the actual size drawn to scale. So I've blown it up here just so that we can kind of see that it's from the center of this object to the center of this object, the Earth. But let me draw your attention to something. The extra distance that we would add for the radius, I guess you will, or half the distance of this 1 kilogram hanging mass versus the distance between the surface of the Earth to the center of the Earth is negligible. Okay, this extra amount of distance here is nothing compared to all the rest of it. So we can actually go ahead and just ignore it. And in this case, we can use the radius of the Earth because the radius of the Earth plus half the distance of a 1 kilogram mass is essentially still just the radius of the Earth. Okay, so we're plugging into our formula. So we've got the absolute value of the force of gravity, which is equal to big G times m1 times m2 divided by r squared, which would be that thing right there. Okay, So let's take a look here at how our units cancel out. We've got meters times meters, and so that's meters squared, so that part goes away. We've got kilograms times kilograms, so that can cancel kilograms squared, and we'll be left with newtons, which is the correct unit for force. So we know that we set this up right. So here we've got the force is equal to 9.8 newtons if you type all of this into your calculator correctly. Well, that 9.8 should maybe look familiar to you. Remember that the force of gravity is equal to mass times the acceleration due to gravity, right? So we're saying that we've got 9.8 newtons is equal to the mass here. That's going to be the mass on the 1 kilogram object. That's this one right here. And again, that's because that's what the question asked us. What is the force of gravity on the 1 kilogram object? So we would have 1 kilogram, and if we were solving for the acceleration due to gravity, we would just be dividing by 1 kilogram on both sides. So that cancels out, and then the acceleration due to gravity comes out to be 9.81 meters per second squared. Now I just added that 1 in just now because that's the actual value, but of course, you know, in terms of this problem, it's just 9.8 meters per second squared. Okay, so let's talk about how to solve force problems. We're going to have the same steps to solving any force problem we ever come across. So let's go ahead and take a look at what those are now, and then we'll come back to this question here in a second. Okay, so here's how to solve any force problem. First, you want to draw your free body diagram. Then you'll write the F-net statements in the axis of concern. That's the axis that you actually care about, the one that contains the variable that they are asking you to solve for. The first F-net statement is going to be Newton's second law. Remember, that one says force equals mass times acceleration. And you'll need to be specific about what acceleration, and what I mean by that is it'll either be the acceleration in the x-axis or it'll be the acceleration in the y-axis until later on in the semester, and then I'll throw another type of acceleration in there at you. Okay, then the second F-net statement is going to be the sum of all the forces in the f-axis. The reason that it is equal to both of these things is because that's what I've already told you the F-net is equal to. We saw earlier that F-net was Newton's second law, and we saw that right here. The net force is equal to mass times acceleration. And then we saw right here that the net force is when all the forces are added together. So we're just writing down both the things that F-net is equal to. Then we're going to set those two equations or statements equal to each other and then solve for the unknown variable. Okay, so here's a problem. A 2 kilogram cart is pulled with a 3 Newton force. What is the acceleration of the cart? Okay, so first of all, this is going to be an applied force because the person is pulling on the cart. If you say that this is a string here, then you might call this a tension force. And then the acceleration is going to be in the x-axis because that's the direction the cart is moving in, the x-axis. Alright, so step 1 is draw your free body diagram. Okay, so just like we practice in class, you draw your x and y axis first. Okay, so then you're going to put your free body as a dot in the middle of the x and y axis. Sometimes it's useful to write what the mass is, right next to that dot on your free body, just so that you'll remember you have it. Okay, and then you're going to go ahead and list all of the different forces. Remember, there's only two kinds of forces in the whole universe: contact and non-contact. So you'll notice that right here the cart is making contact with the surface. That means the surface is going to push up on the cart at 90 degrees, and that's going to give us a normal force. Okay, so we've got a normal force there. Then we have the person pulling on the cart there, so we're going to have an applied force to the right. And I don't see anything else touching the cart, so that means we can move on to field forces, and the only field force is going to be gravity pulling down on the cart. Okay? Alright, so we did step 1, we've drawn our free body diagram. So step 2 is going to be to write our Fnet statements. Okay? So we're going to say Fnet in the x-axis, because that's the one we care about, is equal to mass times the acceleration in the x-axis. Okay, we've got the mass is 2 kilograms, and we're trying to find the acceleration in the x-axis. Then the second Fnet statement in the x-axis is going to be the sum of all the forces in the x-axis. Okay, so here is the x-axis, and all of the forces are the force applied. Okay, so we're just going to have force applied, and that's equal to 3 newtons. Then the next step is to set those two statements equal to each other. So we've got 3 newtons is equal to 2 kilograms times the acceleration in the x-axis. And now we want to solve for the acceleration. So we will divide by 2 kilograms on both sides, and then solve for the variable that we want to know. That's step 4. So we're going to come up with 1.5 meters per second squared, and now we need to take into account sig figs. We were only given 1 sig fig here and 1 sig fig there. This is a perfect 5, which means the arcane rounding rule comes into play, and we round to the even number, so we're going to say 2 meters per second squared is the acceleration in the x-axis. And that's how you solve any force problem. Free body diagram, write both the Fnet statements, set them equal to each other, and then solve for the variable that you're looking for. Okay, so when we're solving force problems, one of the first things we want to do is to draw a free body diagram. So let's learn how to do that first. A free body diagram is just a way to draw a picture that shows all the forces that are acting on a body. And of course, a body is just any object that we are looking at the forces on. It may be that we're trying to calculate what the forces are on the body, or potentially what the acceleration of that body is, or we could find the acceleration and then plug it back into kinematic equations and find velocities and times and all that kind of stuff. Alright, so here's how you do it. First thing you want to do is draw an x and y axis on whatever that free body is. So let's say that I have, a car. So here's my fancy car, and it's going to be, driving in that direction, or maybe it's a cart and somebody's pushing on it. Okay, so let's see, somebody is pushing on that cart with 2 newtons of force. Okay, so if we were going to draw a free body diagram, we let the free body be a dot, and then you draw an x and y axis with the dot at the origin. Okay, and then you always draw your forces on the free body as vectors, and they need to be heading away from the free body. So here we have 2 newtons of force that someone is pushing on this cart with, but really if we were drawing it so that the force is heading away from the free body, we would draw it in this direction. Okay, pushing with 2 newtons would be the same thing as pulling with 2 newtons of force. So we would, have an applied force equal to 2 newtons. Okay? And then there are other forces acting on that free body. Remember, there's only 2 kinds of forces. There's contact and field force. So if we're talking about all the things that are touching this cart, obviously whatever's generating the applied force is touching it, so that's one of our force vectors. And then the other thing that's touching the cart would be the ground here. And the ground is going to supply us with a normal force. Remember, normal means perpendicular in physics. So it's going to apply us with a force that's 90 degrees to the surface. So some force that's pointing in this direction. So we could draw in our normal force vector. And then there's nothing else touching the cart. So now we check for field forces. And the only kind of field forces we have would be gravitational, magnetic, or electrostatic. So gravity would be the one acting on our free body, so we would draw down a force of gravity vector here. And that is the end of that free body diagram because there's nothing else touching it, and that's the only field force acting on it. Okay, so let's see if we can draw the free body diagram for the cart on this table here. Okay, so we're going to draw our x and y axis with our free body as a dot in the center. And then we want to draw our force vectors originating away from it. So we need to ask ourselves about the contact force and the field forces acting on the cart. So obviously we have a person pulling on it, so that's going to be, you could either say it's an applied force, but since they've said that it was being pulled on by a string, we really know that's going to be a tension force. So we've got a tension force acting in this direction. Okay, and then the tabletop here is touching the cart, so that's going to supply us with a normal force that's perpendicular to the surface of the tabletop. So there's our normal force. And then there's nothing else touching the cart. Now, another contact force that we could have would be friction. And friction would oppose the motion. And friction comes from the fact that the cart is touching the surface there. It comes from the normal force. But since they didn't mention anything about that, we're not going to include it. So then we move on to field forces. And so then that's going to be gravity, which always points down towards the center of the earth. And then since forces are vectors, we really should put our vector notation over the top of the forces just to signify that. Okay, so here's a question. A 5 kilogram box is pulled to the right on a frictionless table with a force of 32 newtons. Find the normal force and the acceleration in the x-axis. Okay, so let's see here. We've got a box on a table. It's being pulled to the right, and the force is 32 newtons. And let's see, this is a 5 kilogram box. And there is no friction. Alright, so we want to draw a free body diagram, and the box is obviously going to be the free body. So we draw our coordinate system with our dot in the middle, and now all the contact forces. We've got an applied force of 32 newtons, and then we've got a normal force from the tabletop that's going to be pointing up, and then we've got the force of gravity pointing down. Okay? So now that we've got our free body diagram, we need to do our FNet statements. Okay? Now the thing that we're looking for is the normal force and the acceleration in the x-axis. The normal force happens in the y-axis, so that would be the axis of concern to solve for number 1. And then the acceleration in the x-axis obviously happens in the x-axis, so that would be the axis of concern for problem number 2. That means we're really going to have to do FNet statements for each axis, one for problem 1 and one for problem 2. So let's go ahead and see if we can find the normal force by doing our FNet statements in the y-axis first. Okay, so we've got FNet in the y-axis is equal to mass times the acceleration in the y-axis. Now, if we look at this box here, it's being pulled in the x-axis, which means it's going to slide across the countertop. It's not moving in the y-axis, which means there's no acceleration there. So this is going to be 0 newtons. Okay, so then let's do our second FNet statement in the y-axis. We've got the sum of all the forces in the y-axis. So in the y-axis, we've got the normal force and the force of gravity. The normal force points in the positive direction, and gravity points in the negative direction. So you can say normal force plus negative force of gravity, that's the sum of the forces, or we know that adding a negative is the same thing as subtracting, so you could say the normal force minus the force of gravity. So I think that's what I'll do, the normal force minus the force of gravity. And then we set them equal to each other. So normal force minus the force of gravity, that's the second F net statement, is equal to the first F net statement, where they equal 0. Now I'm trying to solve for the normal force, so I need it to be on one side of the equal sign by itself. So we're just going to go ahead and add the force of gravity to the other side. That means that the normal force is equal to the positive of gravity. And gravity has its own formula. Gravity is equal to mass times the acceleration due to gravity. So that means the normal force is equal to the mass times the acceleration due to gravity. That means we can plug in our 5 kilograms times 9.81 meters per second squared, and we get 49.05 newtons. Okay, now let's see. With sig figs, there are 2 sig figs in the mass, so that means our answer can only have 2 sig figs, so we end up with 49 newtons as our normal force. So that's the answer to question number 1 there. Okay, so now to figure out what that acceleration is in the x-axis. Again, same process. We've got the free body diagram, so the next step is to do our F-net statements in the axis that we care about. And so this time it's going to be the x-axis. And that's going to be mass times the acceleration in the x-axis. So that's going to be 5 kilograms times whatever the acceleration is. We don't know that yet. And then the next F-net statement is the sum of all the forces in the x-axis. So here's the x-axis, and all the forces in it are the force applied, which means that the F-net in the x-axis is equal to 32 newtons. So now we set both equations equal to each other. So we've got 32 newtons is equal to 5 kilograms times the acceleration in the x-axis, and now we just need to solve for that acceleration. So we'll divide both sides by 5 kilograms. This cancels out, and we end up with 6.4 meters per second squared. And that has the correct number of sig figs, so that's the answer to number 2 up here. Okay, so how about another Newton's second law problem? Example number 5. A 5.2 kilogram bucket is pulled up with a force of 18 newtons. What is its acceleration when there is no air resistance? Okay, so first thing we always want to try and do is draw ourselves a little picture here. So let's see, we've got a little pail here, and we are pulling up on it, all right, with a force equal to 18 newtons. And we are wondering what is the acceleration of the bucket. Now, since we're pulling only in the y-axis, that means we're looking for the acceleration in the y-axis. Alright, so what do? We obviously need to draw our free body diagram, right? So we're going to say, okay, here we've got our bucket, which we're going to represent as a single point, the center of mass, and the force of gravity is going to act downward from that center of mass, and we've got a rope up here that we're pulling up on, so that's going to be a tension force. So we're going to pull upward with a force of tension, and that force of tension is this right here, this 18 newtons. Okay, and we know that the force of gravity is equal to m times little g, and we know that that little g is going to be negative. Alright, So Newton's second law, that's going to be our F-net statements, right? So we're going to say F-net, and again we're only in the y-axis, not the x-axis. So F-net in the y-axis is equal to two things. Alright, the first one is Newton's second law, mass times the acceleration in the y-axis, and then F-net in the y-axis is also equal to the sum of all of the forces in the y-axis. Alright, so we've got a tension force that's pointing up here, and we've got a force of gravity that's pointing down. So if we set up our standard coordinate system so that the positive x-axis is here and the positive y-axis is here, then we can say, alright, this positive force minus this negative, or plus a negative, or minus the magnitude of that force there. Right? So we're going to say that we've got our force of tension minus the force of gravity. Okay? So that's going to translate into the force of tension minus mg. Now in this case, the little g over here is going to be positive because this negative sign here represents the fact that this vector is pointing downward or towards the negative y-axis. Okay, and remember, little g is a positive number. Okay, and this negative sign here is only about direction. Alright, so now we just need to set those statements equal to each other. So we're going to say the mass times the acceleration in the y-axis is equal to the force of tension minus mg, or the acceleration due to gravity. Okay, so what are we looking for here? We are looking for that acceleration in the y-axis, this overall acceleration here. That's this piece. So we need to divide both sides by the mass. Alright, so the acceleration in the y-axis then is equal to. Now, one special note here, you cannot cancel the mass here in this term. Alright, that's not possible because this is not multiplication or division here. This is addition or subtraction, so you can't do that. Alright, so don't be tempted to. Okay, so we're going to say 18 newtons, that's our force of tension, minus, then we've got 5.2 kilograms times the acceleration due to gravity, that's going to be 9.81 meters per second squared. And we will divide that by our mass, 5.2 kilograms. Okay, so let's get out our calculators and see what that comes out to be. And as it turns out, we get negative 6.3 meters per second squared as our acceleration in the y-axis. Now, what does this negative sign here mean? It means that the overall acceleration is pointing downward. Alright, so even though they are pulling upward on this bucket with an 18 Newton force, that does not mean that the bucket is actually moving in the upward direction. It means that this bucket is too heavy for the person lifting it, because they're not pulling hard enough upward on the bucket. So the bucket is actually still like sliding downward. Maybe the rope or whatever is sliding through their fingers and is actually still falling down, even though they're trying to pull up on it. Alright? Or maybe they're lowering the bucket down to the ground from the top of a building. But when you lower something down, you are still pulling upward on the rope itself. Alright, if you weren't pulling upward on the rope, it wouldn't be taut. There would be slack in the line, and that's not the case when you lower something. So even if they were lowering it down, they're still pulling upward on the rope itself. But in any case, this bucket is moving in a downward direction. Okay, so the vector for the acceleration in the y-axis would actually be pointing down. That means that the net force would also be pointing down, because net force and acceleration always move in the same direction. Alright, example 6. You are in a hotel on the 18th floor. The fire alarm sounds. You go to exit your room, but remembering the laws of thermodynamics from the chemistry class you took, you place the back of your hand near the doorknob and feel that it's hot. Convection, playa. So you cannot leave your room. The only way out is through the window. You open the window, but the drop would kill you. You have an idea. The bed sheets can be torn into strips and tied together so that you can climb down safely. There's just one problem. Your mass is 60 kilograms, and the tensile strength of the bed sheets before they will rip is 500 newtons. What acceleration down the bed sheets must you have so that they will not rip and you can make it to the ground safely? Alright, so in this problem, we see that there's a multi-step process here that's happening. These bed sheets are going to rip if you allow them to have your full weight on them. So you are going to have to let the bed sheets kind of slide through your fingers as you make your way down to the ground safely. Alright? So we need to identify what the free body diagram is. You are the free body in this problem. Okay? So you've got the force of gravity that's pulling down on you. And remember, the force of gravity is what gives you your weight. Alright? And then we've got the bed sheets pulling up on you, right? Because you're holding on to them. So the bed sheets are pulling up on you, and so they've got a tensile strength equal to 500 newtons. That means that at the exact moment that it reaches 500 newtons of force, they will rip. Okay? So we're going to set the tensile strength there to 500 newtons so that right at that point, that's when they would break. All right? Now we'll do our F-net statements now that we've got our free body diagram drawn. By the way, we don't have an x-axis here because you are only moving up or down, so your y-axis motion only. Alright, so first F-net statement. Okay, so F-net in the y-axis, always use Newton's second law, so that's going to be the mass times the acceleration in the y-axis. Alright, and then our second F-net statement in the y-axis is equal to the sum of all of the forces in the y-axis. Alright, so we're going to do our positive or upward force minus our downward force. Okay, so let's see, that's going to translate into the tension force minus mg. Alright, so now we just want to set those two equal to each other. So we've got mass times the acceleration in the y-axis is equal to the tension force minus mg. Alright, so all we need to do is divide both sides by the mass, and we can figure out what that acceleration in the y-axis has to be so that you will survive. Right? So we're going to say 500 newtons minus 60 kilograms times 9.81 meters per second squared. And then we need to divide all of that by our 60 kilograms. Alright, so I'm coming up with negative 1.476, so on and so forth, meters per second squared. And then, of course, we need to take into account our sig figs. And right here we've got 60 kilograms, It didn't have any kind of a decimal point or anything like that, so that means there's only one sig fig there, so we can only have one sig fig in our answer. And that very first sig fig is right here. Remember, always look one place value further and see if it rounds your last sig fig up. It does not, so that means that the answer is -1 meters per second squared. Alright, so you would need to move down the bed sheets at 1 meter per second squared towards the ground, and that would keep them from ripping and you'd be safe. Alright, let's do the next question. Okay, now we have what you might consider a special kind of Newton's second law problem. We call them elevator problems, and that's because they use what we call apparent weight. Alright, now the reason that we say it is an apparent weight is because depending on the motion of an elevator, the object inside can appear to change their weight. Alright, and that's because of the upward and downward acceleration in the y-axis. You could have more g's on you or less g's, as they say, and when we say g's, we're talking about units of the acceleration due to gravity. Okay, some multiple of the acceleration due to gravity. So, and remember, the force of gravity is what gives you your weight. So your apparent weight it could look like you weigh more or you weigh less, depending on whether or not the elevator is causing you to experience more or less g's, or that is some multiple of the acceleration due to gravity. Alright, now when they ask you for the apparent weight in a elevator problem, they're asking you for the normal force. Okay, that's what they want to know. The apparent weight is the normal force. Alright, it's also kind of a little hint or shortcut is to remember that, let's see, how should I put this? Let me see, we'll call this a hint. Alright, an object moves opposite to the acceleration. Okay, so imagine you've got, you know, an elevator here, and let's say the elevator, you press the button and the elevator starts moving up. What do you feel like when you're standing in that elevator? Okay, if you're standing in that elevator, you feel like something just pushed down on you. So you moved opposite to the direction of the acceleration, right? Now let's say that, you know, you're standing in that elevator again, but this time the elevator starts to move down and you experience like weightlessness, or so it seems. So you feel like you get lighter, so you actually feel some kind of an upward force. Okay, so it's opposite to the acceleration of the elevator. So that's kind of a neat little thing to remember for these elevator problems. Alright, so let's start working this out. We've got a 150 Newton person. Now remember, since they gave us newtons, that is the force of gravity, which is the weight of the person, not the mass. Okay? Newtons is for weight, kilograms would be for mass. Alright? And they are standing on a scale, like a bathroom scale, in an elevator that's going up at 3.2 meters per second. What is his apparent weight? And remember, they are asking for the normal force if they are asking for the apparent weight. Alright, so as always, we're going to draw our scene here, our picture. And let's see, we've got a little bathroom scale here, and this person standing on it. Alright, now let's see, the elevator is going up. Okay, so the acceleration in the y-axis then is equal to a positive 3.2 meters per second squared. Okay? Alright. Now, the person has a force of gravity acting downward on them, and that is equal to 150 newtons. Alright, so let's do our Fnet statements. Okay, so Fnet in the y-axis, we'll always do Newton's second law first, so that's equal to the mass times the acceleration in the y-axis. And in this case, we have the acceleration in the y-axis, that's this 3.2 meters per second squared. It's the mass that they did not give us at this point. That doesn't mean that we don't actually have it though, okay? We have this 150 newtons down here. Remember that Fg equals to mg, right? So we know that 150 equals m times g, and we know that little g equals 9.81 meters per second squared. So we can just rearrange to solve for the mass by dividing by little g on both sides, right? So we can say m is equal to 150 newtons divided by 9.81 meters per second squared. Okay, so we come up with 15.29 kilograms. Of course, there's more decimal places than just that, but I'm not going to include those for now. We should when we type them into the calculator, and we definitely will, but I don't want to write them all out. Okay, so that's our first Fnet statement in the y-axis. The next Fnet statement in the y-axis is going to be the sum of all of the forces. Okay, so let's see. What are the forces? Well, we've got this force of gravity acting downward on the person, right? And then we've got the person is standing on this bathroom scale. So that means that the bathroom scale is going to be supplying some kind of an upward force, this normal force that we've talked about, right? That normal force is a contact force. Since the person is contacting the bathroom scale, it must be supplying a normal force. So we're going to say then that it is the normal force minus the force of gravity. Remember, as we said in these elevator problems, that's what we're looking for, is that normal force. Okay? So this translates into normal force minus 150 newtons, because that is the person's weight. Okay, so now we just set this stuff equal, these two equations here equal to each other. So I'm going to go ahead and multiply this out before I set it equal. Okay, so I'm getting 48.929, so on and so forth. And then let's see here, we've got kilograms times meters per second squared. That's going to be a force, so that means the unit here is newtons, is equal to the normal force minus 150 newtons. Okay, so that means that I need to add 150 newtons to both sides so that I can figure out what that normal force is. Okay, so I'm getting, let's see, sig figs. This one has 2 sig figs. That's got 2 sig. Alright, so 2 sig figs it is. So, let's see, that means I'm getting in my calculator 198.929 newtons. Now, we want to do the right sig fig. So let's see, there's the first significant digit, there's the second one. We always look one place value further and ask, does this one round that one up? Well, yes, it would. So that means we would get 200 newtons. But if we write it like that, there's only one significant digit here. And we must have two significant digits. The only way to do that is with scientific notation. So we'll say 2.0 times 10. Now let's see, the decimal place is really right here. We want to move it behind our first sig fig. We had to move it twice to do that, so that means we have it times 10 to the second, and then we'll need our unit here. Alright, so the apparent weight then, the normal force, is 2.0 times 10 to the second newtons, or